This is the third chapter of the video pamphlet on agonist efficiency. In the first chapter, we defined efficiency in terms of the weak and versus strong binding energy ratio, shown by the blue lines here. And in the second chapter, we showed three patterns of efficiency, the last of which is that there are modes and there are classes, and the classes of modes are the same, shown here by this chart, this bar diagram here, which is either the spectrum or the barcode for a binding site. And now, in this chapter, we're going to backtrack and try to understand what are the biophysical origins of efficiency. Why is there an efficiency class in the first place? Why do several agonists share the same efficiency? And again, we're going to start with an unexpected experimental result. This came from two studies, one way back in 1901 by Claudio Grossman and another by Toppin Nyack in 2017, which was much more thorough and quantitative. The result that was surprising was that binding to the closed state, this was measured directly in single channel measurements from kinetic measurements, binding the association rate constant, which is K on, to the closed channel is slower than diffusion and agonist dependent, whereas association to the open state was close to the diffusion limit and less agonist dependent. So K on to C is below diffusion, slower than to O, and correlated with affinity. That is, K off, the off dissociation rate constant, to C is approximately constant for these four agonists, which all span a very wide range of affinity, from ACH being the highest affinity and efficacy to choline being the lowest. Now, the reason this is a surprise is because we thought, like everyone else, that ligands diffuse into their binding sites. So we expected something like this, that the binding to C would be roughly at the diffusion limit, and the same for all of these ligands, which have the same diffusion constant, and that binding to O would be the same for all but much slower because loop C closes over the binding site. That's the general thought. That seems to be a consistent observation, that loop C closes over the binding site when you have a strong agonist in it. But that's not what we observed. What we observe is this, and it's a real observation. It's profound. It's robust. It's for these four agonists, but not only this is for the alpha epsilon site, but also for alpha delta and the fetal alpha gamma site. The same pattern holds. So this is a robust finding that needs to be explained. So how do we explain this? So for this, we're going to focus on the C binding profile and describe a reaction coordinate called catch and hold. This is in the spirit of Michaelis-Menten. We are going to start insert an intermediate state in the binding process in order to account for that apparently slow on rate. So before 1955, this is how people viewed receptor operation. You added an agonist to C and you got it O and it was bound. That was the concept of affinity by T.J. Clark in 1925. That was taken from enzymologists and chemists. So in 1955, Del Castillo and Katz came along and said, well, just like Michaelis-Menten, there's an ES state, there's an AC state here. I'm going to use an asterisk to denote an intermediate state that was not observed. It was just a hypothetical state at that point that described efficacy. It counted for efficacy where you could saturate a binding site but still get different levels of output. So that was stolen directly from Michaelis-Menten and Victor Henry, that there's an intermediate state in the activation of receptors. And it wasn't until 20 years later or 25 years later that Cahoon and Sockman actually detected it in single channel. The patch clamp was invented, and they were able to discrete it. Much as Britton Chance invented the stop flow apparatus and detected the S state, Cahoon and Sockman used the patch clamp to detect the AC state. All right, a few years after that, in 92, I believe it was, I proposed that there is an intermediate state in the gating reaction as well. It was hard to detect, it wasn't quite clearly there, but I went on to use another technique, a new technique, not a new method, but a new an analysis technique called phi-value analysis, to say that there are four of these things inside of the gating reaction. And that was around all in the early 2000s, and shortly thereafter, around 2009, this group shown down below, both at University College London and Mayo Clinic, used very high resolution clean recordings in order to detect a very fast closed shut state that they called flip or prime. And that, I think, as I will describe in the next chapter, it relates to the four intermediate states that were proposed by phi-value analysis. So there are intermediate states in the activation process, particularly in gating. And now I'm going to first I'll name these. I'm going to name the not the state, but the event that connects states. So AC is connected to the first intermediate by a transition that I'm going to call hold, and that switches the binding site from the C type to the O type. And then there are other events taking place in the isomerization that we will discuss later. So hold is the switch of the binding site from the low to high affinity conformation that takes place at the onset of the gating reaction. I'll justify all this in the next chapter, but I'm just giving you the name hold now. But now, in addition, so these are the affinities associated, the equilibrium dissociation, the constants associated with those states. Now I'm going to propose there is another intermediate state in the binding process that separates diffusion and a conformational change that leads to the low affinity state AC, and I'm going to call that event catch. Notice that I'm naming these by the process, not by the state. It's the process that connects the intermediate states that are called catch and hold. So catch is a local rearrangement that lets the agonist into the binding site to give weak binding, and hold is another local arrangement of the binding site that takes place in gating that produces strong binding. Now, these guys have been detected experimentally, AC and these guys. The one between diffusion and catch has not been detected experimentally, and it probably it'll be hard to do so because that state separates two events of the same conductance. It's very hard to tell that apart, particularly when it's in the microsecond time scale. So these guys separate different conductances, and therefore that's the reason they were detected in the patch clamp. It's probably going to take some new technique or maybe computational technique in order to identify that intermediate state between diffusion and catch. But now we can add to that a different affinity. There's a super low affinity state called KD-APO, I've called it, which leads to, in sequence, precedes the low affinity state, which then precedes the high affinity state. So just to keep in mind that this model predicts there are 3 affinities, not 2. But catch and hold are the only things that we need to worry about between agonists. The fusion constants for the agonists that we're using are about the same, and everything that happens following the hold event in gating is about the same for all agonists. So difference between agonists only depend on differences in catch and hold. That is the model of the catch and hold model. So let's apply that model to our efficiency plot, which you will recall is a plot of log efficacy divided by log affinity, the slope of which is related to efficiency, and each line is a discrete efficiency class. So if catch and hold are all that matters when it comes to differences between agonists, then really what this plot is a plot of hold energy versus catch energy. So this is log KDC, that's catch energy. This is log L2, that's hold energy, because the rest of the isomerization is just an offset. There are offsets due to diffusion in this. This is plus an offset energy for the diffusion, which is the same, and this is hold energy plus an offset, which is from the rest of the isomerization. But the slope of the line is the same because the offsets are the same for all the points. Remember, each point here is a different agonist. It's from a different dose response curve. So that is interesting because hold is something taking place inside of gating and catch is something taking place inside of binding. So the implication of efficiency, namely a linear relationship between efficacy and affinity, the implication of that is that there's an energy change inside of gating that's correlated with an energy change inside of binding, which means binding and gating energies are linked. They are not independent. They're different processes. When you think of binding, you think of a ligand going into the binding site. And when you think of gating, you think of the receptor changing its conformation globally. So they are different processes, but they are energetically linked. Something is happening inside of binding that is linearly related energetically to something that's taking place inside of gating. So this is a sort of a profound change in our thinking about binding and gating. We're used to thinking these as being separate processes, but in fact, they are two stages of one process. So agonist efficiency is the strength of the catch and hold energy link that is at the heart of receptor function. Insofar as binding is converted to gating, chemical energy converted to mechanical energy, that is the heart of how ligands activate receptors. And this slope of this line, which is efficiency, is at the heart of that. It illuminates the heart of the drug-induced activation of receptors. So let's continue on that, and we'll focus on the catch and hold linear free energy relationship. So now we're going to draw an energy landscape just for the agonist-dependent parts of this reaction. We've gotten rid of the fusion. We've gotten rid of the rest of the isomerization. We're just going to hold on this energy link process of catch and hold, and we're going to draw an energy landscape for that. So here's the energy landscape for catch and hold, with the first hump being catch and the second hump being hold, and they're being connected by a straight line. There's a linear free energy relationship between the two. So the orange bar represents the energy change in the catch part of this reaction, and the purple bar represents the energy change in the hold part of this reaction. And the sum of the two is the energy of catch plus the energy of hold. Well, let's write these energies down. The energy of catch is just log KDC. The energy of hold is log KDO minus log KDC. That's the difference between the two, because hold is the switch from low to high affinity. And if you take the sum of these two, you just get log KDO for the whole thing. So now you can see the fraction of this energy change, total energy change, KDO, that came from hold, which is that which determines efficacy, is just this pink equation here, KDO minus KDO over KD minus KDC over KDO. So there's our pink equation giving you efficiency, which is the midpoint of this curve. Efficiency is where the middle of this curve is. It's the fraction of the overall energy change that is going to hold. And the key here is why do different agonists of different efficacies and affinities have the same efficiency? Why is there an efficiency class? Is because these two are tethered by a line. And this is now a weak agonist, which has a different total energy, you can see, but you'll see that the efficacy and affinity are variable, the lengths of these lines and the difference between the lengths of these lines, but the ratio between the two lines stays the same, which means the fraction of the total that's purple, the fraction of the purple over black is the same ratio for both strong agonists and a weak agonist. So that's the linear free energy interpretation of why there are such a thing, why there is the origin of efficiency classes. And efficiency just depends on where that point is in the reaction coordinate. with things that are to the right there meaning less, and things to the left meaning greater efficiency. But so the conclusion from this is that catch and hold are connected by that dotted line in a linear free energy relationship that crosses binding and gating. Catch is in binding, hold is inside of gating, and that dashed line covers both, connects both. That's why catch and hold are connected. And the implication of that is that catch and hold, this event between catch and hold, is this energy landscape here is the first link in a conformational cascade that connects binding and gating. So all the way from the formation of the pre-catch condition, which is KD-APO, through KDC, KDO, is all one giant conformational sweep, conformational cascade that is linked by linear free energy relationships. So that's the profound, I think, implication of efficiency, is that the implication is that that binding and gating are two stages of a unified cascade. That it's not even though we draw them as separate events, they are energetically linked. So let's break this down one step more. So I'm going to now show you how I imagine the energy landscapes changing during the catch and hold reaction coordinate. So there are our three intermediate states given by asterisks, and this would be the APO condition without any agonist. The agonist, the first state is the agonist promotes catch. So the agonist shows up. I have a little schematic of just the binding site shown down below, and that binds with that KD-APO affinity. And when that happens, the agonist promotes catch. By promotes, I'm again stealing this from enzymologists who find that substrates stabilize transition states, that the agonist stabilizes the transition state for catch and allows catch to happen. So that's shown by these three little cartoons down below. The agonist stabilizes the transition state so that catch can happen with a higher probability. And then the next step, of course, is that catch promotes hold. This is the key event, that once you're in catch conformation, which is bound with low affinity, that stabilizes the transition state of the next structural event, which we don't know what that is. I'm just drawing it here as a compaction of the binding site. Various things happen. We don't know what that is, but something happens, and then that allows hold to happen with a higher probability to give you KDO. So agonist promotes catch and catch promotes hold, and that catch promoting hold is the crosstalk between binding and gating that is efficiency. So this mechanism that where each step lowers the transition state of the subsequent step, of the next step in sequence, I'm calling a zipper mechanism, because that's how zippers work. When you form this a cross link between these two ties, these two hooks, it brings the next one in sequence closer together. That means lowers the transition state for the formation of the next link. So the next link is far away, it gets closer because of the formation of the one before. So that's why I'm making the analogy that this is a zipper mechanism for conformational change. So this brings us to the end of the section on the origins, the biophysical origins, which is the catch and hold linear free energy relationship. So binding to Z involves a local arrangement at the agonist binding states, and energy changes in catch, part of binding, and in hold, part of gating, are linked. So activation is a single conformational cascade. There are binding and gating are separate stages of that. Catch and hold are substages within that, and there are probably sub-substages to be discovered in time. But there is a single energetic sweep of conformational change. Well, the question arises briefly, is this just something that happens in acetylcholine receptors? And as I said at the outset, the acetylcholine receptor has been a fabulous model system for all receptors essentially since the time of Galvani. But we can now, there is a little bit of data that suggests that maybe this happens in other receptors as well. And these plots are taken from this paper shown here in the lower left. You can find the citations in there. We took from dose response curves, we took efficacy and affinity measurements and plotted them in our efficiency plot form. And we see that there are generally straight lines. So here's a GABA receptors. This is from Trevor Smart's lab. There was a lot of data in that paper, analyzed very thoroughly at the single channel level. You can see there is a general straight line, which implies efficiency. If there's a straight line, that means it's an efficiency class that gave 39% efficiency. There were a couple of outliers that were determined statistically, and perhaps these represent a separate efficiency class, which is lower. That was given by red. So that's true for these other receptors to some extent or another. There's not a great range in some of these, but I want to point out muscarinic receptors also seem to have two different efficiency classes. In fact, this data was used as an example of showing how efficacy and affinity are uncorrelated, because they would not be if you viewed these as a single class. But when you separate them out to classes, you see, and we separated again these statistically. This was not any arbitrary thing. We used statistical methods to identify outliers, different groups. So we get again 52% for the blue group. Something less than that, maybe it would be 42%, or maybe it's a 35%. I don't know what it would be. But the key is, since the things that follow hold are the same for all agonists, that means you can have downstream events that are the same for all agonists, just represent an offset in this plot. They do not change the slope of this plot. So even though you're doing downstream signaling with G proteins and potassium channels and whatnot downstream from this, if that's the same for all agonists, then it will not affect your efficiency plot. So you may be able, it looks like efficiency plots it's worth trying to see if they work for GPCRs as well as ligand-gated ion channels. And here I'm just taking an example of a glycine receptor which had 3 points that fell on a line, even though they weren't very spread out. We can get an estimate just from these 3 dose response curves. We get an estimate for the unliganded gating constant, which was 8 times 10 to the minus 4th, which looks like 0 in any method, electrophysiology method, and efficiency is 60%. So it's probably not that. It's worth trying this efficiency plot thing. I think from your dose response data for whatever receptor agonist combination you have. And finally, I want to just show you a list of potential applications of efficiency. Of course, in pharmacology, we know it can be used to classify agonists. It may prove to be useful in drug discovery when you can compute max from EC50 and vice versa. If it's it may be able to assign receptor subtypes based on that barcode, and perhaps modulators act by changing efficiency. In physiology, it's possible, as I showed you with a congenital myasthenic disease, that maybe that could be the common feature of mutations of certain diseases. If you have ancillary subunits or membrane effects or post-translational modifications, could be acting by changing efficiency. Whereas you can get a change in the efficacy and a change in the affinity that are, you could have the same affinity and a different efficiency, and that would be maybe the cause of the disease. It looks like you've broken the machine in some way or increased the machine's efficiency. Of course, we want to know the structural basis of efficiency, what determines efficiency classes and efficiency modes. We think that's going to be related to discrete C and in particularly O structures. Catch and hold are related energetically. That means they must be related structurally in some way, or probably related structurally in some way. And that's going to be important to determine out what these two events are. These are not states, these are processes. And where are those ultra-fit low affinity binding sites that determine that APO binding constant? We need to find those, because that's the event that triggers everything that follows. And finally, maybe understanding efficiency will help us with allostery. We may be able to map activation pathways, understand if this conformational cascade, which was previously called the gating conformational wave. I'm calling it cascade because it incorporates now a binding event called catch, and the zipper mechanism of sequentially lowering transition states. Maybe that will be useful in understanding allosteria in general, and that is going to be the subject of the last chapter of the pamphlet, which is on implications.